Okay, so welcome to the lecture 54 in this course Classical Mechanics 1. In this course, last few lectures we are discussing two-body central force problem. Particularly in last lecture, we were discussing the Kepler's problem. So let me just recap what we were doing in last lecture. So in two-body central force problem, we have two constraints of motion. For example, let me write first the Lagrangian, so it will be clear. So Lagrangian was half the reduced mass, if you recall, r dot square plus r square theta dot square minus ur. So this is in general a Lagrangian for two-body central force problem, and you can notice I mentioned repeatedly that theta is cyclic, and any central force problem theta is cyclic, leading to the conservation of angular momentum. So theta is cyclic. Angular momentum. Okay. So we can calculate this p theta is del L del theta dot, which is half mu r square to theta dot. Okay. So this means that mu r square theta dot is constant, and that we denoted by angular momentum m. Okay. So this is one constant of motion, and another is the total energy that we wrote earlier. The total energy is also a constant of motion. So this expression, let me get back to that. It was total energy was half mu r dot square plus m square to mu r square plus the potential energy u of r. So these two can be integrated, and integral from the integration you can find the solution to the problem that we discussed. That for Kepler's problem we solve this integrations. Let me tell you the final result which we obtained. Kepler's problem, you have u r was minus alpha by r, and for minus alpha by r we perform these integrations and we find the solution. So we'll start from the solution. So it was 1 over r equal to 1 over p plus 1 plus e cos theta minus theta 0. So this is the solution we obtained in last class, where p and e we consider as p was m square mu alpha, and e was root over 1 plus 2 m square e is the energy of the particle, mu alpha square, mu is the. So all these things we discussed last time. So today's class will start from here. So let me recap again. So what we did, we were considering two-body central force problem and two constant of motion regarding the angular momentum and total energy, and from here you can integrate using this relation. You can integrate for theta and r to find the solution. Okay. So, and that integration we did in last class, and we have found that this is the solution. Okay. And you can always choose your coordinate system or without any loss of generality, by choosing your coordinate system, you can consider theta 0 equal to 0. Okay. So, let us simplify this further. 1 over r is 1 over p, which is defined is m square by mu alpha times 1 plus e, which is also defined root over 1 plus 2 m square e by mu alpha square times cos theta. So, this is the equation we will consider, and we will see for various cases how this gives the trajectory of the particle, and we will matching this with our qualitative analysis from the behavior of the effective potential. Okay. So, let me write E is 1 plus 2 m square E by mu alpha square. So, suppose your energy E is greater than 0. Okay. Suppose your energy E greater than 0. So, in that case your E will be, the small e will be greater than 1, because all things are positive here. Alpha is positive, mu is the reduced mass, of course is positive, and then angular momentum square. So, everything is positive. So, if E greater than 0, capital E, total energy is for positive total energy, the E, that eccentricity. So, this is this you can see this is a equation for conic section, and E is the eccentricity. Okay. So, E will be greater than 1, and E greater than 1, the this will represent hyperbola. So, now recall that drawing of the effective potential versus r, and we found that for 1 over r potential this was like this. Okay. So, here we have E greater than 0. So, this correspond to E greater than 0, and particle will have a this kind of motion will come and will return back to infinity, and with the smallest approach from the center of force. So, this is completely matching with our qualitative analysis and the directly solution of this. Okay. So, for E greater than 0. Now, let us consider E less than 0. So, this is case 1. Case 2, we have E less than 0 for negative energy. So, negative energy, so this term, so for E less than 0, this term will be negative. So, this term will be negative, and your small e eccentricity will be less than 1, implying that this will be a ellipse. Okay. Eccentricity less than 1, this equation will represent equation for ellipse. Okay. So, ellipse. Now, what information we obtain from our plot of U effective. So, you remember U effective, let me write you m square by 2 mu r square minus alpha by r. So, this was the our U effective. So, now less than 0, you will have two turning point, because it will cut in two places to the. So, particle will have motion, but this is in general, but for Kepler's problem you will have a ellipse. So, that also we can find that from our qualitative analysis an exact solution is matching. Now, let us consider the third case. So, third case will be E equal to 0. Suppose your energy is equal to 0. So, energy is equal to 0 means this. So, it will have only one turning point, and this turning point is here, because it is cutting the U effective at least only at one point. E equal to 0 also means that your eccentricity is 1, because look at the expression E equal to 0, this term will be 0. So, this term will be 0 and you will get eccentricity equal to 1. Okay. So, eccentricity is equal to 1 implies parabola. Okay. And the other possibility, the fourth possibility, is that if the energy is equal to the minimum of the effective. So, fourth possibility, if the energy is negative and if the energy is negative and equal to U effective minima, then we said that the motion will be circular. From the quality of analysis, we said that it will be a circular motion. Okay. So, circular trajectory. So, what will happen in our eccentricity formula? Just recall, this eccentricity was root over 1 plus 2 m square E by mu alpha. Let me check, mu alpha square rather, mu alpha square. So, now E you are saying okay. So, for circular motion eccentricity should be 0. So, that will happen only when 2 m square E by mu alpha square equal to minus 1. That means, E equal to mu alpha square by 2 m square. Okay. So, in this energy you will have eccentricity will be 0 and circular orbit. But now we have to check whether this is the energy for the U effective. So, now we will check. This is the value of U effective minimum. Okay. So, that we can check. Once we have done this, then we are through that all this analysis of Kepler's problem. Okay. So, let us try to see whether the minimum of U effective is this value. So, U effective expression, let me write again, mu m square to mu r square minus alpha by r. So, to find a minima we have to find this equal to 0 at say r equal to r 0. So, implies minus m square mu r 0 q plus alpha r 0 square. Okay. Implies this will have value r 0, we will find value of r 0 from here, and r 0 will be, so r square cancel. So, r 0 will be minus plus alpha mu by m square. R 0 will be m square, rather m square by it will be minus m square mu r 0 equal to minus alpha. So, R 0 will be m square mu alpha. Okay. So, at this point minima will happen. Okay. So, let us consider that whether it is a true minima or not, or at this point what is the value of the energy. So, that, and one can calculate the double derivative and find that this will be the true minima, but at least we can find U effective at r equal to r 0 will be m square 2 mu r 0 square. So, r 0 is m to the power 4 mu square alpha square minus alpha by r 0. So, m square by mu alpha. So, what will happen? This mu alpha square by 2 m square and minus mu alpha square by m square from the second term. So, you can immediately find it is minus mu alpha square by 2 m square. So, which is exactly same for which the eccentricity becomes 0. So, if the energy, if E equal to mu alpha square by 2 m square, then small e equal to 0, eccentricity equal to 0. Okay. So, you can find that the orbit will be circular. Okay. One can of course check that del 2 U effective del r square greater than 0 at r equal to r 0 for a true minimum. Okay. So, the summary of this part is that we can solve Kepler's problem, we can find a analytic solution of the integral of motion. So, integrals of motion can be solved exactly for Kepler's problem, which is very important because this describes the Earth's motion around the sun. This also can be applicable to the electron's motion around the nucleus. So, Kepler's problem, and we found the trajectory is completely same as we have opted from the qualitative analysis from plotting the U effective. Okay. Okay. Here I just want to mention that this problem can also be solved, this Kepler's problem can also be solved from this orbit equation dtu d theta square, you remember, equal to u minus mu m square u square plus f of 1 over u. So, this is the orbit equation between r and theta, that u is 1 over r. So, equation between u and theta is the orbit equation, and one can solve this equation for f corresponding to your u, which is minus alpha by r. So, for this you can find your f, put this f here and solve this equation, and from here also whatever solution we get from integrating the motion, the two equation which is coming from the conservation of angular momentum and conservation of total energy, you will get the exactly same picture. Okay. So, this will conclude the teaching part of this two body central force problem. Now, we will consider, we will solve few problems. So, let us start solving few problems this remaining time of this class, and in the next class will be as a tutorial class. So, this remaining time, the next class and remaining time of this lecture will solve some problems related to two-body central force problem. Okay. So, let us consider one by one. So, we will consider several problems. So, problem 1. So, let me write, so that the force that will cause a mass m to describe a circular orbit which passes through the center of describe a circular orbit which passes through the center of force. Center of force varies as inverse fifth power of r. Okay. So, this is the problem, and so problem says that there is a central force which has caused a mass to move in a circular orbit, and that circumference of that circle passes through the center of force. So, if you have such situation that a circle, so first we have to find the equation of the circle. So, solution. So, for a circle of radius a whose circumference passes through the origin. This is purely from geometry, is given as r equal to 2a cos theta. Okay. So, this is the equation for a circle whose circumference passes through the origin. Okay. So, this is given, and then you have to find what will be the F r in the central force problem. So, what you have to do, you have to use the orbit equation d2 d theta square plus u equal to minus m square. This equation just I wrote mu by m square. Okay. So, mu by m square u square f of u. So, this is the orbit equation. So, you have to calculate f of 1 over u will be minus m square u square by mu times d2 u d theta square plus u. Okay. So, what is your u? U is 1 over r, and that is 1 over 2a cos theta. Okay. So, we can find the du d theta, which will be 1 over 2a, and okay. So, 1 over 2a cos theta whole square times 2a sin theta. Okay. That means 1 over 2a will get cancelled, sin theta by cos square theta minus no, there will be a minus from here and there will be a minus from here. So, will be cos theta by sin theta, and so you can write this is 1 over 2a sec theta tan theta. This in from trigonometry you can write this, no problem. Okay, so now d2u d theta square, if you calculate, you can calculate 1 over 2a sitting outside. Tan theta is so sec theta tan theta derivative will be square theta, and for the these terms sec theta tan theta times theta. Okay. So, you can have this 1 over 2a, let me write sec q theta plus sec theta tan square theta. So, d2u plus d theta square plus u will be 1 over 2a common, and u is nothing but 1 over 2a sec theta. Okay. So, it will be this is sec q theta plus sec theta tan square theta plus sec theta. So, this will be 1 over 2a sec q theta plus sec theta, if you take common 1 plus tan square theta, and this will be sec q theta. Okay. So, 1 over 2a sec q theta. Okay. So, now this will substitute in the equation of f of u. So, if you substitute this, we calculate is proportional to sec q theta, and there is also a u square. So, you will have and f of u. So, let me write. So, f of 1 over u will be proportional to u to the power 5, because this 2a times 2 sec q theta, right. This is sec q theta, this will be sec q theta. So, this will be 2 sec q theta. So, this sec q theta, but u is 1 over 2a sec theta, right. So, this is u cube and there is a u square. So, it proportional u to the power 5, that means proportional r to the power minus 5. Okay. So, with this maybe we will stop this lecture, and next class will be a tutorial class, and will solve few others problems. So, next class will start with solving problems. Okay. Bye for now.